Problem number 5. So we've got some sinusoidal graphs here. We want to state the amplitude, the period, and the midline. I think it might help if I draw the midline in first. We can either visualize it, or we might be able to use those formulas we had come up with. Let's see, just to add a little bit of scale here, I think this must be -1. I can see the -2. Here's -3. -4, -5. So it looks like the top of this thing is at -1. The low point is down here at -5. I think even visually you can see that halfway between those two numbers is right here at -3. If you wanted to use the formula for the midline was the one where you average the two numbers. So -1 plus -5 is -6. Cut that in half and you get -3. So the midline is definitely y equals -3. The amplitude will be the distance from that midline up to the top or bottom. So it's this distance right here. And you can tell that that would be 2 units upward. So the amplitude would be 2. Now for the period, I need to look left to right. I'm trying to figure out the smallest distance of x before the entire graph starts repeating itself. So if I think of this as the starting point, how far do I have to trace along here before this hill and this valley starts over? It looks like right here I'm about to then get another hill and another valley and so forth. So that means the period of this graph is pi. Okay, let's take a look at the second one. Looks like here this is 3, here would be 1, -1. So my highest spot is 3. My lowest spot is here at -1. If you add up those two numbers, 3 plus -1 makes 2, and half of 2 is 1. So here would be the midline right here at 1. Y equals 1 would be the equation. The amplitude is this distance here. That's obviously a distance of 2. So the amplitude would be 2. And the period, this one's maybe a little trickier. Here's the initial spot at the y-axis. It doesn't appear to be a very nice spot. Nonetheless, though, I can still trace along. I was wrapping up the hill, then getting into the valley, and I'm going to start over right when I get to here, because here I would be, again, just wrapping up the hill again. Well, so that means the period is going to be 2 pi over 3. If you don't like that, another way that we could have done this would have been to just look at this high point, and I know the graph is going to repeat again once you get to this high point. I could figure out the distance between those two values, and that must be the period. Well, the ending spot is 3 pi over 4. The starting spot there was pi over 12. If you just subtract these two numbers, you should get the period. The common denominator would be 12, so I'd have to change this to have a 12 on the top or bottom. That's going to give me 9 pi over 12 minus 1 pi over 12, which is 8 pi over 12. And if you reduce 8 pi over 12, you've got a common factor of 4 in each of those. You get 2 pi over 3. That's another way we could have obtained it. In problem number 6, we want to look back at this first graph from number 5, and we want to say what the phase shift would need to be if we were trying to write an equation for this graph using each of these basic shapes. So part A says regular cosine. The key is I need to find that basic regular cosine graph in my picture. Well, the regular cosine graph is the vase. I need to identify a complete vase in this picture. Here's where it would be. The thing is, the regular cosine function starts at the y-axis. This one, though, has a vase starting at pi over 4. So I would have to take the regular cosine function and move it pi over 4 to the right. If I did, then it would start where this picture starts. Okay, what if instead I wanted to use the reflected sine function? Well, then I don't want to find a vase anymore. I want to find that basic reflected sine shape. Reflected sine is the valley and the hill. So I'm looking on here for a complete valley and hill. Here's the one I can see easily. Complete valley and hill. Where does it start? It starts at pi over 2. And so if I wanted to use reflected sine, I would need to have a phase shift of pi over 2 to the right. And then the last one says regular sine. Well, regular sine is the hill and the valley, and that one I see right at the beginning here. Here's the hill, here's the valley. Well, this one already starts along the y-axis, which means if I wanted to use regular sine, I would not need a phase shift. Obviously, that means using regular sine would be the easiest choice here. Now, in problem number 7, we want to do the same thing using that second picture from number 5. Again, trying to figure out what phase shift we would need, starting with regular cosine. So I'm looking at this graph. I'm looking to see where I can find the vase. That just means from one high point to the next high point. And I can see that that starts at pi over 12. So I would have to have a phase shift of pi over 12 to the right. Okay, what if I wanted to use reflected cosine in that picture? Well, now I don't want the vase. I'm looking for the ghost. Reflected cosine is the ghost. I'm looking for a low point in this picture. And then the ghost runs from one low point to the next low point. I can see that that starts here at 5 pi over 12. My phase shift would be 5 pi over 12 to the right. And then lastly, if I'm looking for regular sine, let's see, regular sine is the hill and the valley. The first hill I see starts here, it starts right in the middle. You'd get a hill and you'd get a valley. There's the regular sine shape. Well, in order to use that, I would have to move it pi over 12 to the left, since it's over there at negative pi over 12. It looks like for this one there is no easy choice that avoids a phase shift, and that's because here at the y-axis the graph is not a high point or a low point or a midline spot. I would have to use a phase shift in order to write the equation. Problem number 8 is a review of finding vertical asymptotes of functions from algebra. You might remember that vertical asymptotes typically happen where the denominator comes out to be 0. In other words, where the function is undefined. So when I look at problem 8a there, I'm going to concentrate on the denominator and figure out where it's equal to 0. Obviously, that's going to happen when x is negative 1. Well, that, I think, is where the vertical asymptote is. In fact, the asymptote is a vertical line, which means the equation is x equals a number. And so this really, I think, is the answer. Let's take a look at the calculator and verify that. So I'll go to the y equals area. I'm typing in x on the top. And then I'm going to have to put that x plus 1 in parentheses for the calculator to understand that the whole thing is in the denominator. I'm not sure exactly what window to use. In algebra, zoom 6 is often a good choice. It's just kind of a standard viewing window that shows you 10 in every direction. The calculator is not so great at showing the asymptotes. Asymptotes are generally shown as dashed lines, but I think you can still see that it's here. And it looks like we got it right. It's right here at negative 1. There's this line that the graph gets really, really close to. It never quite makes it there. Of course, it can't make it there because if you tried to stick negative 1 into the function, it wouldn't exist. It comes out to be undefined. But the vertical asymptote would be this line at x equals negative 1. Letter B, again, if I can just figure out when the denominator is 0, I'll have my answers. This one's a little bit more complicated. I'll have to solve it using factoring. Let's see. This was somebody's FOIL problem. X times x would make x squared. Looks like the back is going to need a 3 and a 2. The middle one would come from the 2x and the 3x. It's going to have to be a minus 3x and a plus 2x. I think if I FOIL that out, I'll have back to where I started. And then I use the zero product principle. Either this one is equal to 0 or the other one is equal to 0. And if I solve both of those, I have my answers, and I think I have my asymptotes too. Looks like this one has 2 vertical asymptotes. One of them is at x equals negative 2, and the other one is at x equals 3. Let's put up a quick picture. So back in the y equals, I've got 5 on the top, and then the denominator again in parentheses, x squared minus x minus 6. I'll go to that same viewing window, so I'll hit Graph. And sure enough, you can see there are two vertical asymptotes this time, one happening at positive 3 and the other happening at negative 2. The last one I think I can do in my head. It's pretty obvious that the only x that would be bad here would be x equals 0. And so we must have a vertical asymptote at x equals 0. We can draw a picture quickly here. 10 over x is the equation. And when I hit the graph, sure enough, the only asymptote is right here along the y-axis, where the equation is x equals 0.